Hi, my name is Noah Bates, and this is my experimental thermocouple project for ME341. A little background on this project was basically taking a thermocouple and a microcontroller and comparing the voltage values it read against an analog thermometer that we think is correct or that we know is correct using two uh, temperatures or events that we know the temperature of. Experimental method, here is my setup. Here's my microcontroller, my thermocouple, the wire connected to it. This is yellow one. We have an ice bath, a pot of boiling water. We know the ice bath is at 32 degrees. Boiling water is 212 degrees. And then we dip this thermocouple into the ice bath or into the water or just hold it in ambient air. And we know the temperature of it. So we take the analog thermometer, put it in the ice bath. We should say it's 32 degrees Fahrenheit. Put in the boiling water, should say it's 212. And we can compare the analog reading against the thermocouple reading. Values of the thermocouple are put in this microcontroller, which are sent to the computer. So every time we run a test, I could read the temperatures from the microcontroller using my computer. So the calibration data versus manufacturer's curve. The calibration data is the voltage read from the microcontroller compared to the analog reading for that voltage. So we put the analog thermometer in boiling water, got a reading of 200 degrees Fahrenheit. Then we put the thermocouple in the water. We got about 1.65, 1.7 volts. Same thing for freezing water. Freezing water, we put the analog thermometer in, got about 34 degrees. For 34 degrees, we got 1.2 volts. Manufacturer's curve is the orange curve. That is the calculated values of temperature based on the read voltage. So that's provided by the manufacturer. So obviously we can see the thermocouple is reading very low. For freezing water, it's close. It's reading 1.2 volts and maybe around 30 degrees or between 25 and 30 degrees Fahrenheit. But the boiling water, it's the same voltage. Boiling water is reading around 130 degrees Fahrenheit, which is way lower than it's supposed to be. Boiling water is at 212 degrees Fahrenheit. The air fraction. So this test was done doing dipping the thermocouple in water, starting the test just so we can know what the thermocouple is reading for that temperature. This is done with starting the test while the thermocouple is in air and then dipping it in water that is a different temperature. So we can see the ambient temperature here, and then there's a sharp decline where it changes, and then into the freezing water temperature. This is to determine the air fraction and the time constant. So here we have the natural log of the air fraction on a graph. This is before any smoothing was done. As we can see, the data is very scattered. After smoothing, we have a time constant of 0.0931 seconds for first trial and 0.0467 seconds for the second trial. This trial 2, time constant is about half of trial 1. However, they are very small. It's less than a tenth of a second, which I'd say is pretty good. I work in industrial engineering, and we have PLCs that can, their time constants are very quick. They're close to something like this. But like I said, they're a little different, but I think that's okay. And then it's possible for the thermocouple to be more accurate than the thermometer. In this case, no, because the thermocouple is reading so much lower than it should based on the manufacturer's curve. I'd say it's not accurate. I'd say we are much more likely to rely on the analog thermometer. And then, is there a practical way to determine the accuracy of the analog thermometer? I think the exact way we did it was pretty good. It was pretty close to, we'll go over this here, it was pretty close to the freezing temperature was 34 degrees, even though it's supposed to be 32. Boiling water was a little bit off. I'm not sure if the analog thermometer just has a harder time with higher temps because it's reading 200 when it should be 212. But like we said, in conclusion, the thermocouple is very inaccurate. The analog thermometer is much more accurate based off of this table here. We can see it's pretty close. But again, this graph just shows that the thermocouple is very, very poor in reading the right temperature. It's extremely low, about 100 degrees Fahrenheit lower than it should be. Reflection. Once calibration, the thermocouples, I think, are very useful. They can be used in a lot of fields. Thermocouples are used where I work. We have heat lamps that we use, very strong heat lamps that we use for chemical curing onto parts. and some very old machines, and we're not really sure what the temperatures are on those sometimes because they're on 50-year-old machines. So we use thermocouples. We install thermocouples, plug those into a computer, and from that computer we can read whatever temperature those heat lamps are doing, because we don't want to be too high. It'll burn the material off. Don't want to be too low, and it's not going to cure on the part correctly. And then the second thing I learned from this project is calibration is, I think, pretty easy with the right tools. I think the way we did it was very well. We had a freezing ice bath, which we knew the temperature of, boiling water, which we knew the temperature of. And once you have that, you can compare the analog thermometer to that. It was pretty close. We can adjust the analog thermometer to be at the right temperatures. To set to be 32 or 212 degrees Fahrenheit. And then we can use, once that analog thermometer is calibrated, we can use that thermometer to then calibrate the thermocouple, which is very off. Because of how wrong the thermocouple was, I'm not sure if we can actually calibrate that to get it to read correct values. The lower voltage, lower temperature values were pretty close, but as we can see in this graph, the higher temperature, it's 100 degrees Fahrenheit off. I mean, even if we say at 1.7 volts, it's supposed to be 200 degrees Fahrenheit. I think there's just a high enough inaccuracy where I wouldn't really trust the thermocouple, at least this one, to read any of my temperature values. But other than that, this is a great project. Thank you very much for this semester. Have a good one.